Hello, welcome everyone. It's a pleasure to be hosting another webinar. Today we have a special guest and actually quite special topic that was chosen because we have been receiving a lot of support requests on this topic. So the special guest is Dr. Gemignani. You may already know her. If you do not know her, Jessica has been collaborating with NIRx for a very long time. She's actually a biomedical engineer with a degree from Pisa. She has done then her PhD in Berlin at the Technische Universität Berlin with the topic of multivariate fNIRS analysis, and she keeps her research work in fNIRS analysis with Dr. Judith Gervain in Paris still, right?
Yes.
Okay. Yeah. Okay. So today we will be talking about actually mostly second level analysis because we realize that every time we speak about analysis, we always focus on first level analysis, and then we briefly touch on second level only at the very end, and actually that's where most people have questions on. So we focus on second level analysis, in particular then on how to use covariates. So how to use this, let me call them regressors, and how to use it practically, really. So Jessica will first show you a few examples. Really, she will show you a few studies of what kind of application has been done in this study and what kind of covariates have been used and why. And then she will show you a practical example of how to use this covariate in the NIRS toolbox. And just as a few logistics notes, so you're all muted and you have a question box where you are very welcome to type your questions at any time. We will be collecting, so you see that we have Blanca and Ashling at the team as well. I'm Lamia, you may know us as well already. We will be monitoring the questions, so please feel free to ask as many questions as you have, and we will have some time, so we kept it around half an hour at the end for Jessica to answer all your questions. So we will try, of course, to cover all questions, but there may be not enough time depending on how many questions you have. Okay, that's pretty much it. So Jessica, you can start. Thank you very much for helping us with this. Yep.
Yes, thank you for inviting me. It's very nice. So I'm going to share my screen. Yes, so yes, today we are going to talk about the second level analysis of fNIRS with the covariates indeed. And so first of all, we are going to see some introductory information. Why do we want to use covariates? And we're going to see a few examples from recent literature. And we're going to see how do we include, like, what's the theory behind including the covariates in the analysis, so the ANOVA or the mixed effects model. And then we're going to have a practical walkthrough of analysis case with the Brain Analyzer toolbox. So first of all, this is really introductory, but it's just really to set the ground on the terminology that we are going to use today. So whenever we run an experiment, what we want to do is to test the effect of a certain intervention on, or a certain stimuli, for example, on some measure. And typically, so this measure is the outcome variable, also called response variable, also called dependent variable in statistical terms. And in our experiments we are talking about, so the outcome variable is typically some measure of cerebral activation in either oxy or deoxyhemoglobin. So we run the experiment and then we perform a statistical analysis because we want to explain our dependent variable, for example, the activation in a certain area of the cortex, in terms of other variables that are called this time explanatory variables or independent variables, predictors, regressors. So an explanatory variable is really any variable that we think might affect the outcome, either because it is manipulated by us, so as in terms of the experimenters, or not manipulated by us. And this is the case of any characteristic related to the participant. So of course, like, the task is an explanatory variable that is purposely manipulated. But then there are also all these participant characteristics like age, gender, IQ, the ability to perform a certain score that it's not purposely manipulated in the experiment. And as much, so when we recruit, of course, we follow strict recruitment procedures to limit as much as possible the variability across subjects. Okay, so for example, we exclude subjects with a certain condition or outside a certain age range. But as much as we'd like to rule out variability and we'd like our sample to be really homogeneous, there are going to be inevitably some differences between the participants. So the goal of including this information in the analysis is really to, first of all, control for it. So remove the effect of, for example, age or gender from the analysis, but it can also be that we are interested in the effect of age or gender or IQ. So the covariates can be either of interest or not of interest, or we just want to control for it. So, for example, just to mention a few examples from literature, in their work, Stojanovic and colleagues, I hope I pronounced it right, they wanted to determine the pattern of neural activation in the orbitofrontal region of the brain in patients with multiple sclerosis during a working memory task. And the task employed was the MBEC. We are all very familiar with it. And they recruited, of course, also a control group of healthy individuals to compare. And here in the table that I took from the paper, you can see the participants' information. So in this case, of course, the only predictors of interest were the condition itself, the task, and then the groups. But the age between the two groups was very inhomogeneous. So in order to ensure that possible group differences would only be related due to the disease and not to age-related differing physiology, then they entered the age of the participants as a covariate. In this case, as you can see, the covariate was not really of interest per se, but it was entered to remove a possible confound from the statistics. Another case, this is not the only meaning of covariate, as I said. In another study that I selected from Vassina and colleagues from last year, they wanted to compare the activation in the dorsolateral prefrontal cortex when individuals were presented with basically, they were warned beforehand whether the task was going to be easy or difficult, and so they wanted to check to investigate the correlates of anticipation of difficulty. And the task was mental arithmetic, and they had also several questionnaires, and in this case they entered really several covariates related to the performance of the in executing the task, the reaction time, even the mood before the experiment, the mood after the experiment. So they entered many covariates, and some were confounds and some were actually of interest. As you can see here in the figure that I took from the paper, they plot the activation, so the accuracy as a function of activation difference the activation difference between difficult and easy task. So it is not the case that covariates are just something that is entered in the model to control for it, but it is instead any continuous variable that can be put in relation to the outcome sensibly. So I say sensibly because to mean that you need to have an explanation why you think the covariates has to do with the outcome. Of course, we cannot not just enter anything into the models, but we need to have an hypothesis why the covariate we are entering, we think it is relevant, conducive to the activation. A third and last example is our work that actually indeed we did at NIRx when we wanted to analyze the performances of 3 different algorithms. Then before comparing them, we checked that these performances were actually independent on the characteristics of the subjects. We wanted to exclude the fact that they were depending on the characteristics of the subjects. So in this case, we used like age, hair color, gender, and also the time of measurement, because the chronobiology has been reported to play a role also in the cerebral metabolism. And indeed, we found that in one case, one algorithm, its accuracy was actually lower in brown-haired subjects, which makes also sense. So this was something that we needed to take into account later on. So these are examples of how you can use covariates in your analysis. It can be because you think it confounds another variable, or you can be because you are actually interested in the effect of this covariate. And another thing I would like briefly to mention is covariates at first and at second level, because we call them covariates and that's it, but the concept is absolutely no different whether we are talking about first level covariates or second level covariates, because in the first case we want to see if the whole individual time series is affected by a concurrent time series. A concurrent time series can be an accelerometer that is often used to track the occurrence of motion artifacts, but it can also be any other physiological signal that is being concurrently measured and that we think may have an effect on the NIRS time series. For example, some works, some works have used the temperature of the nose tip as a measure of autonomic nervous system activity. So at first level, you run the model, usually the GLM, and then you get a beta value for each condition of the task and a beta value for each additional covariate. And this is it is interesting, of course, also to look at this alone, at these covariates alone, because they can carry a lot of information. For example, if you used an accelerometer and the model returns a large beta value for the covariate accelerometer signal, then it means that the signal explained much of the NIRS. So probably there was a lot of movement on the subject's part. It is really up to the experiment whether you want to do the statistics also on the beta of the concurrent covariate or not. It depends on the statistics, on the experiment, sorry. But basically, so why I said it applies both at first and second level. So I said a few times concurrently. It is important to keep this in mind, also in relation to the difference between first and second level covariates, because so at first level, the observations are the time samples. So for a covariate to be entered into the model, it needs to have as many time samples as the time series that we want to explain. So this is where the covariates at first and second level differ. At first level, the number of observations is equal to the number of time samples, while at second level, the number of observations are actually the number of subjects. So you have each subject contribute a beta value for each condition. So in this way, basically, so for each subject, I'm going to have a beta value for like condition 1 and condition 2, condition A and condition B for subject 1, and then subject 2, condition A and condition B. So in this case, I need to enter in the second level statistics, not really a time series for each subject, but instead a subject-wise value and additional information for the individual. So this is why at second level, we don't use time series anymore, but single values like age, gender, IQ, individual scores. So how do we include covariates in the statistics? There are several ways, of course. Covariates can be entered in an analysis of variance. So in that case, the ANOVA becomes an ANCOVA, an analysis of covariance. Of course, they can also be entered in linear models, either fixed effects models or mixed effects models. So usually we get this question like, where is the ANOVA different from the mixed effect model? When should I use one or the other? So all things being equal, the ANOVA or ANCOVA and the mixed effect models should yield the same answer. So if there are no missing observations, the fit is performed with the same method, the same type of sum of squares, there is no imbalance between groups, there is no imbalance between conditions, then they should yield the same answer. In reality, mixed models are always to be preferred. First off, because they handle much better these possible imbalances that I just mentioned. It's often the case that for example, there are a different number of participants in groups. Okay, this is very often, but we can also have, for example, missing data. For example, one subject performed really poorly on only one condition, but not the other, and we want to keep the other. So we're going to have a huge imbalance. So the mixed models can really, or for example, again, sorry, missing data can also result from discarding bad quality channels. So in all these cases, mixed models handle the statistics better than the ANOVA. But furthermore, the mixed models, they're mixed in that they don't only model fixed effects, but also random effects. We are going to come back on this later. So we can also model, for example, random intercepts and random slopes that account for the variability in how participants contribute to the outcome, or the variability of how a covariate is modulated within each participant. So mixed models are more powerful than an ANOVA or an ANCOVA. The learning curve is steep, but they are better, and they are more general. They represent the general case. Of course, there are differences in the mathematics, but the ANOVA, the t-test, they can all be regarded in some ways as specific cases of mixed models. So this is what we're going to use today. So as Lamia mentioned, we are going to have a walkthrough with the Brain Analyzer toolbox or NIRx toolbox. You need to download it, you need to unzip and add to the MATLAB path, and you can download it from the page of Dr. Appert on GitHub. If you're not super familiar with it, or you need to refresh some concepts, there are many videos and tutorials available in the NIRx Help Center, also given by Dr. Appert himself. So there are a lot of resources there. So sign up for this Help Center, because there are many resources where you can learn more. So the first thing to pay attention to when using the NIRx toolbox is really the structure of the data folder. You need to organize it according to the proper hierarchy. You need to already have in mind what you want to do at second level. This is always the case. Even when designing the experiment, you need to have in mind how to analyze it then. What's the statistics more or less gonna be. But in this case, you really need to know already what you want to do, because since you're most probably, because when loading the data, the demographic information are going to be gathered according to how the data is organized inside the folder. So since you're most probably interested in group comparisons, individual subject folders must be placed within each group folder. So you're going to have a huge data folder, and then subfolders for the groups, and then within each group the participants folder. You can have as many levels of hierarchy as you like, as long as you define it later on in the loading step. And if you also have, for example, repeated sessions with separate measurements for each subject, so each subject undergoes separate measurements, and you need to model it in the statistics, then your hierarchy will look something like groups, sessions, subjects, individual files. So as you can see here on the left, I have also a demographics Excel file, but let's talk about this later. This can be placed anywhere on the computer. You don't need to place it there by all means. So we load the data by specifying, as I said, the organization of the data folder, which is group and subject. As you can see, it loaded 68 subjects divided into groups. There are 34 subjects per group. And you may know this already, the resulting row variable contains as many data structures as many subjects, and it displays all these fields, so description, info about the probe, info about the design, and so on. Importantly, each subject has a field that is called demographics, that includes possible demographic information about the subject and its group membership. If we create the demographic lookup table now, we see that for now we have nothing. We have only the group membership and the subject ID. We are going to add some demographic later. And then you can inspect the data. For example, this is subject 1. You can, just to see the design, we have one condition with 2 labels, A and B, and you can type raw.draw to draw the data along with the stimulus design. The probe is this one on the right. You can draw it this way. So this data was taken from the NIRx Toolbox website. So it's not data that we acquired personally or that I acquired. Is the data, is the demo data of the NIRx Toolbox. And yeah, there are a few channels missing. It's not perfectly symmetrical between the two hemispheres, but yeah, there are a couple channels missing. Anyway, so if you want to plot just a small, if you want to plot the probe in this way, like with the mesh and with the mesh of the brain and the scalp, you need to change the default draw function with these lines of code. And if you don't know how to extract the mesh, you can look into the registration demo of the NIRx Toolbox. It explains line by line, really, how you can achieve this figure. So as I said, there was no demographics, so we need to add some further demographic information to be used at second level. So there are two ways of doing this in the toolbox. You can either code it in the script by defining the vector with the covariate. Here, for example, I defined the age as a random distribution between 4 and 10 years, and then I added it manually by calling raw.demographics, and then I added the field age. And this is a way, but clearly you need to manually pay attention to the order in which subjects have been loaded. You need to pay attention to the fact that the order needs to be matched, of course, by the vector, okay? There is another way. It's cleaner and also less error prone, especially if you have many subjects, because you can have an Excel file, as we were seeing before, a demographics CSV file, and with a column with the participant ID and the info that you want to associate. In this case, I want to associate age again. This is cleaner for two reasons. One, because you don't need to pay attention to the order of subjects, because this module here, NIRS.modules.addDemographics, will do it for you. So you only need to tell what's the name of the variable to be matched. In particular, here I specified subject as the name of the variable to be matched. But it is also cleaner because let's say you already loaded all the data and you pre-processed and even did already the first level statistics, and then you realize that you had additional information on the subject that you didn't include immediately. You don't need to start over. So you can append the new demographic information to the first level statistics variable, and we are going to see this later today in the demo. So also, covariates can be kept in this way separate from the analysis script, which is a bit less error prone. So this method, I think, is a bit better. So we're going to go really fast on we loaded the data. We're going to be fast on the pre-processing because it's not the topic of today, but I just want to mention that there is this NIRS.modules.default modules.single subject that allows you to define all in a batch all the pre-processing steps that you want to follow, and then you can also specify what do you want as an output. Like, for example, here I specify that I want I will give as input raw, and then I want HB, so hemoglobin, and I want, of course, substats, which is the first level statistics results. I want them, and everything else is going to be not kept in the workspace. So as I said, I just wanted to mention that before using these modules is a really nice feature to have this batch capability, but you need to carefully check the default options, not because they are wrong, it's just that they may not work for everyone's case. For example, the most obvious is the DPF in the Beer-Lambert law. Normally, by default, it's set to 0.1 because it includes also the partial path length. path length factor, which is totally valid, but you need to know that you are using the partial path length factor, also because it's something that you may not necessarily want to do, and then also because then you wouldn't know maybe where the order of magnitude comes from. So also the canonical basis function, by default, it is set to peak at 4 seconds, I think, and normally most people want 6 seconds, so you need to change the default. This is the only thing I wanted to say, but you can customize it and run it in a single line, specify which variable you want to keep, so it's a nice feature. So the result of the subject level statistics, let's look just at one first level result. We had 35 channels spread across the scalp, and now we get 140 coefficients because we have 2 conditions and 2 components, so oxy and deoxy. So it's 35 by 4. To navigate the results and know which p-value belongs to what, you can look up the variables field here. So if you call substats.variables, as you can see, the first 2 rows belong all to the same channel and are oxy and deoxy, so they alternate this way, and also that the whole first half of the coefficients correspond to condition A, and then the second half to condition B. Just keep this in mind in case you want to extract values and work on them independently. You can see how they are organized this way. Also last thing to notice is that there is also a field with corrected p-values. So the field Q contains p-values corrected with the Benjaminian-Hochberg procedure, also called the false discovery procedure. So you can plot again on the same mesh that I've shown before. You can plot the statistical results. For example, here I wanted t-values in the range -10 +10, and I only wanted those having a corrected p-value lower than 0.05, and so these are the results. And but you can also plot beta values, for example, if you want them instead of the t. Okay, so we finished the first level statistics, and now it's time for the group level. So as I said, mixed effects models are to be preferred. In the toolbox, there is a function, it's called NIRS.modules.mixedeffects that can use any info already stored in the subject level statistical results to build the model. So there is no need for you to re-prepare a table. The module will gather all the necessary information from the first level statistics. So importantly, this module is built around another function, the MATLAB built-in function called fitLME. And I really strongly recommend anyone to read the documentation page on the MathWorks page, because it's very informative, it's rich with explanations, examples. It's a very good place to start to understand how this module works. So basically, a mixed effects model tries to explain the dependent variable, which are the beta values from the subject level statistics in terms of factors, just like we did at first level. It is called mixed because there are, as I said, fixed factors and random factors. So there are many formal definitions, but basically fixed factors are all those factors for which, if you repeated the experiment, you would use the same levels. So condition is clearly a fixed factor because you would use the same stimulus design, most probably. Random effects are all those effects for which, if you repeated the experiment, a different set of levels would apply. So, for example, participant ID is a random factor because it refers to participants. And in general, all the factors related to participants are random because they depend on the participants. Okay, so this is the formulation for the single channel. So one step further, because on top of all this, in the toolbox, so I'm not going to go into much mathematical detail here, but in the toolbox they developed an implementation that takes into account not a single channel, but all channels simultaneously. And this is in order to compute the covariance model of the noise, considering all channels together. So this is quite a sophistication, and again, I'm not going to go into much detail here, because the formulation is very well laid out in the paper from Happer's lab, Santosa and colleagues, 2018. So they also added options for downweighting the outliers, centering the variables, pre-whitening the second level, and so on. Anyway, the model is solved for all channels at a time, and p-values are returned after false discovery rate correction. So this is a very nice feature. The mixed effect module is called also within the ANOVA module. So you may know, so we're going to see this all in practice in a moment. So you may know, so first you need to perform an ANOVA on the results of the mixed models to get main effects and interaction effects. And only if one of those is significant, then you follow up with post-hoc tests and see more in detail where the effects come from. So to do this, the ANOVA module runs mixed models and ANOVA in the same run and outputs an F-test for each channel for each main and interaction effect, which is what we are going to see like as a first step. So we run the ANOVA module. As I said, it is wrapped around the mixed effects module. So you need to specify the formula again in Wilkinson notation, just like you would do with the mixed model. If you're not familiar with the Wilkinson notation, again, the MathWork webpage explains it quite well. And we run this module on our first level stats, and we get a table of results with each channel and component, and then main effect of age, main effect of condition, main effect of group, and then the condition by group, which is what I wanted according to the formula. You see the formula I wrote beta equal to group by cond plus age, and this 1 by subject is the random factor that I was talking about. Here I'm only adding a random intercept for the subject. So let's plot. You can also plot the results again on the mesh, and by calling this group stats probe, you define again the default draw function. I wanted a 3D mesh, and then you specify draw, and again I want only the p-values that after multiple comparison correction are lower than 0.05. This is an F-test, so you don't specify a threshold for T, but you specify a threshold for F. So I want the scale to be 0, 100 for the F value. So for our demonstration, I chose to focus on the effect of group. So you can see here in this HBO by group, HBO group, that there is a very strong effect of group here on the left hemisphere that we want to follow up. So I'm going to see in the lookup table, and I saw that it's source 5, detector 4. And here, so this code that I wrote is just because I wanted to index the table, so that the ANOVA table is quite long. I'm going to index it. First off, I want only those Q values, namely the corrected P values lower than 0.05. And then I go further, and I only want to see the group effect with oxyhemoglobin. So I look for it in this way with this line of code. And then I look at the table, and I see that all these channels show a significant effect of group with oxyhemoglobin, both corrected and also uncorrected, because you can see here from these columns that they are very similar. So, for example, let's focus on this very strong effect here. As I said, it's source 5, detector 4. So I see that it has an F value of 214, p-value super small, and also the corrected value super small. So this is how I would report it. I would report like f for this source detector pair is 214, and then p-value lower than 0.001. So here I want to follow up on this channel. Okay, so basically, let's go back 1 second. Here I only have the main effects of age, group, condition by group, and condition. Okay, but what we want to do is actually to look at whether group 1 has a higher activation than group 2, and so on. So I follow up with a mixed effects only. I rewrite the formula this way. I code exactly the same way, but this time I don't want the ANOVA on it. I only want the results of the mixed effects module. And then I narrow down because I only want source 5, detector 4. And as you can see, you can output a table, so a variables table from the results of the group statistics. And so you see like source 5, detector 4, type HBO, HBR, and the conditions. And here you see that there is only A, G1, age, A, G1. Okay, here I have put this label here, but basically, let's look here. It's only A, G1, age, A by group 1. Why I don't have B, G2, and B by G2? Because it's all in the way I coded the dummy. So here with this job.dummy coding, you specify basically which of the two is the reference. So if you put effects, it's going to take one level out of the two as a reference, and explain G1 and A1 with respect to the estimate of the intercept. While if you put, instead of dummy coding effects, you put reference, you would get B, G2 and B by G2. It's okay, it's exactly the same result. It's only how you look at it. So in this case, we have the variation basically of G2 with respect to the intercept. Okay, so G2, the actual intercept of G2 is this estimate here plus the estimate of the intercept. Okay, so let's move on because, okay, no, I wanted to say something more here. So actually, so as I said, it is all wrapped around the fit LME built-in function from MATLAB. So if you go inside these group stats.variables, you get this table. You can access the single models. So the models as returned by the native fit LME function. And this is very useful because apart from giving you the results here, the estimate, the standard error, the t-value, and the p-value, it also yields the root mean square error, which is a criterion that we want to use to assess the goodness of our model. Okay, we're going to see this also later, but it's a very nice feature that you can access the single models for each channel clearly, because each channel was modeled differently. I mean, within the same model, but each channel has a different linear model. You can access it and check all the diagnostic information about the modeling. So, okay, until here, basically a lot of statistics, but we haven't really talked about covariates a lot. Okay, yes, I entered the age, but so at this point, I enter another covariate, the IQ. So as I said before, there is no need to start over. You can just reload another Excel file and append the new information to the first level statistics. So by doing this, you specify the CSV file this way, you read the table, and then you define this NIRS.modules.addDemographics, and you specify the name of the file and the variable to be matched. So again, I want the new information to be matched on the existing information based on the subject variable. And then you can run, as you can see here from these lines, you can run this job on the subject level results, and you're going to have new subject level results, but this time, I mean, they are the same results. It's only that the demographics include now also the IQ, which you can use in the group level. Okay, so the IQ is simulated, and in particular is completely fictitious. So I'm making this up. So the IQ, I made this on purpose, very dishomogeneous between the two groups. Group 1 has an IQ centered around 90, while group 2 has an IQ centered around 140, as you can see. So this is a case where normally you would need to use the covariate IQ, because you cannot know whether your differences are due to the group or to the IQ. Maybe the groups are due to something else. You group the subjects based on a disease or based on another kind of clustering, but they also happen to have very different IQs. So in this case, this is a case where you would need to use the covariate. So I want to see in particular if the main effect of group at this point holds up in that channel that I was following, because we don't know what the task is exactly. So as I said, I downloaded this data from the NIRx Toolbox website. We don't know if the IQ is actually conducive to a differential activation or not, or if the hemodynamic activation difference is really due to the grouping. So this is what we are trying to discover. So I'm going to run again this model. This time I'm entering IQ as an additional covariate. Again, I call this time the ANOVA module instead of the mixed effects module, because I want first to have main effect of the main effects and the interaction effects, and then only if they are significant, I'm going to follow them up with the mixed effects. So it's the same formula. I'm just adding IQ here as a covariate. Again, I put this scheme for the coding of the dummy variables, and I call the group stats. This time I call it on the subject statistics results after adding the demographic information. So there are two possibilities. Either the task basically depended heavily on the IQ, which cannot be the case since I said that I added it. So either the task depended heavily on the IQ. In that case, I'm going to have a strong main effect of IQ and a lesser effect of group. The second possibility is that the differential activation was really depending on the grouping of subjects, and then the fact that they had such different IQs was only a coincidence with no effects. And so what happens is that I have both. So I have a strong effect of group because that actually lies in the data itself. So the data was designed as to return a strong effect of group. And so it didn't matter that the IQ was equally clustered, that the hemodynamic activation in this channel was still group dependent. But since I have entered a highly collinear variable, IQ, then now the model also attributes part of the effect to this new factor. So I hope I was clear. So there is no effect of IQ. It's not possible because I simulated it. But since I manipulated it as to have such a strong clustering, such a strong overlapping with the grouping, then the model also thinks that the effect is partly due to the different IQ. And this is another problem, is the problem of collinearity. So normally one shouldn't enter in the models variables that are too correlated one another, which was the case clearly in this case. But here you can see that so the model splits in two, so attributes part of the results of the effect to the group and part to the IQ. So again, we can look up the summary table. Let's look again at the source 5 detector 4. So you first I want the corrected p-values, and then I want only the rows showing group as an effect IQ, and I want only Oxy. And this is the resulting table. So you have an F value of 97 for the IQ and 144 for condition for group. Before including the IQ, the effect of group, the F-test associated to the effect of group was 214. So yes, the model basically split the effect in the two. So partly attributed it to the IQ, partly to the group. Both are significant. And now we follow up. Again, before we were only looking at the ANOVA results, now we follow up more closely. We run again the mixed effects with the NIRs.modules.mixed effects. We run again the same formula, but we add the IQ, and this is the lookup table. And again, you can go inside each model and look up the diagnostics of the model. Okay, so you can you have an overview of everything related to the model. Let's look here. Yes, so for example, inside the model there are many fields. As you can see, this is an this is a screenshot from a linear model object, and so don't look only at the p-value to decide whether including a covariate or not. Actually, don't look at the p-values at all, but look at the model criterion, so the goodness of fit measures. So if we look into the field, this field model criterion, we find that indeed the AIC criterion before including the IQ was actually lower than after loading, including the IQ. And the same happens with the BIC criterion. So when selecting the model, one has to aim at minimizing these objective criteria. The lower, the better in this case. So basically, this gives us the double check. Let's say that including the IQ in this case did not improve the model. So when you include a covariate of interest that is sensible and makes sense, you should really see these criteria decrease both substantially. This was not the case. So basically, I came to my conclusions. So you have to enter the covariates that are known to have a correlation to the outcome variable. You have to enter covariates if they are not homogeneously distributed across groups of interest. So that is for sure. And the Brain Analyzer toolbox has methods for mixed effects and subsequent ANOVA and mixed effects only at group level. And it's a good tool for including the covariates in your analysis. And when you want to decide whether including some covariate or not, first of all, it should have there should be an explanation. You should include covariates that are known to have a relation to the outcome. For example, age in many cognitive tasks clearly is related to the outcome. Also the IQ, it can be gender. There are some tasks for which, or some brain activity that is known to be different between different genders, but so add covariates that you have that make sense and check the model fit and the model criteria to see that it actually improves the fit, so you know that it is explanatory of the data. So before ending, I wanted just to recommend some resources that I found useful for myself. So I think I mean, they are really nice resources. So for example, this book, this Statistics Without Math, I mean, there is a bit of math, of course, but discovering statistics. And then there's also this multi-level modeling free online course offered by the University of Bristol. There is this book that is freely available at this link. So there are many resources that I really recommend to look at. So this was it, and I wanted to include a slide with questions, but I don't have it. So if you have any questions, I'm happy to.
Hi again, Jessica. Thank you so much. This is really helpful.
Yeah,
It's been half
a question slide.
Yeah. No, it's been half an hour. I wanted to tell you how I liked very much your comments on how the learning curve on the mixed effects is very steep.
Yes, steep, and I have not climbed it completely myself. I'm not sure. So yeah.
I'm sure many others can testify to that. Yeah.
Yes, but I think there are resources. So as I said, I wanted really, while we wait for the questions, I mean, I really want to stress the point that there are many resources to learn. So take the time and look at this.
Definitely.
Because, yes.
And starting from your presentation, so this is one of the first questions and the one that you always get. We will of course share the slides, right? You're happy with it, so they can access the. Yeah, we will email everyone after the webinar with the PDF of our slides, so you can take a look. So we do already have some questions, so let's start. So the first one, well, do you get some kind of correlation coefficient for the covariates, and that you are basically able to report?
Of course. So if you're using the mixed effect model or any kind of even a fixed effect, if you don't have a random effect, if you're using a model, then you get an estimate for any effect that you are entering into the model. So just like you get an estimate for condition, you get an estimate for group, you get an estimate for age and IQ and any other covariate that you have. So yes, you get an F value and the degrees of freedom, and you report it that way in the paper, in the article. Yes.
Okay.
And it is not really a correlation because it takes into account also all the other variables that you entered. So it's not really a one-to-one correlation. It's a correlation considering everything else. So in a sense, it's more powerful than a correlation.
Okay, thank you.
Perfect. Yes.
I will take the next question. So this question is, could you also say some words about how to specify covariates in the first level, especially in order to account for an equal number of observations and the time sampling? Is that a clear question? Yeah. Okay.
Yes, I see what you mean. So normally the covariates at first level, they're entered just the same. So it's the same concept. It's only I wanted to stress the point of the length of the time series because we get this question often. But you enter it in the GLM, which is a model, so it's a statistical model, and you enter it as a covariate in the GLM. I don't know which toolbox this user is using, but for example, in NIRS Lab, you can add additional regressors. There is really a function to add additional regressors, but even like in the NIRS toolbox, you can define an additional predictor in the design matrix, and you can put your covariate. So as for the length, yes, you need to have the covariate needs to be as long as the time series. If it is longer because you measured it concurrently, but maybe one started a little earlier and one finished a little later, then you can trim in order to achieve the same length. The important thing is that they are actually concurrent. You cannot, of course, place something that was measured in a different moment. You need to place something that was measured exactly at the same time of the measurement. If for technical reasons it is of different length, you can trim some part of the longer time series as long as you don't cut a stimulus. And even if you cut a stimulus, if it's one, I mean, you have to adjust the length. Yeah.
And in that.
Sorry, please go ahead. Yeah, no, please go ahead, Ashley.
Yeah, in that same vein, you'd have to be at the same sampling frequency. So, say your accelerometer samples more, you would then downsample that accelerometer to meet your fNIRS signal.
Yes, because the important thing is that really you can capture the fact that they variate together. They vary together. So you need to capture the fact that they move along together. So they need to be on the same sampling frequency. Yes.
That's exactly, thank you, Ash. That's exactly what I wanted to point out, because that's a question we receive quite often. So the number of samples has to be the same. So I don't know, this is true in NIRS lab, where very often, actually almost always, whatever the regressor is, we are now talking at level 1, right? Covariates at level 1. The sampling frequency is not the same as for the fNIRS. So you will never have the same number of samples. And in NIRS lab, you have to manually resample your data to have the same amount of samples. So I'm not sure if the NIRS toolbox gives you tools to resample, or if this has to be done manually. Yeah.
So I was just saying because I wanted to share, because I think I put a line on the resampling. So just let me see here. Yes, for example, I'm going to share my screen 1 second again. I'm still sharing my screen.
Yes, we see.
Oh, sorry. So, for example, here you can call these NIRS.modules here inside the pipeline. You can call these NIRS.modules.resample, and then you specify the new sampling frequency that you want. And yes, and this is 2 lines, and it's going to resample there.
Okay, that's fantastic, because it's almost never the same. So and it has to be.
Yes, no, definitely. They need to be the same because they need to capture the concurrent variations. So that's important. That's what you actually want.
Yes. Okay, perfect. Next question. We are receiving many. Thank you so much, everyone. Blanca, yeah.
Yeah, here comes another question. Is the Benjamini-Hochberg correction for the number of channels only, or also for the number of conditions and oxy and deoxy hemoglobin?
That's a great question. So I'm sure it's not about the conditions. The conditions are actually part of, so the conditions are levels of the same condition. So it's really actually one time series that you are fitting to the data at the end. It's one time series that is the combination of these 2 levels, right? Condition A and condition B. So it's not so the multiple comparison problem comes into play in a different way, in a different term, namely that the models are, it's the domain. So the models are solved at channel level and component level. So yes, the components should also undergo multiple comparisons if you take them all together. If you want to look at everything, oxy and deoxy, they should also undergo the same multiple comparison, because you are actually performing several. They are all tests that you are performing in parallel, but they're actually independent. So you are considering a different time series all the time. Channel 1 HBO, channel 1 HBR, channel 2 HBR. So these are all statistical tests. Then the condition, no, the condition doesn't have anything to do with this. It is fit to the time series. And so the question, I think, was about whether the it was considering, so the p-values returned by the NIRS toolbox actually take into account both channels, conditions, and hemoglobin. No, it takes into account channels and components, but not conditions.
Okay.
I hope it answers the question, but let me know if it doesn't.
Okay, perfect. We have a few more. We still have some time, so I think it's fine. I will go with this one. In this walkthrough, the same processing pipeline was used for all the individuals in each group, right? And how would you deal with that in the case you need to define different pipelines for each subject, for example, due to different amounts of motion artifacts? That's actually a really interesting question.
So I'm not sure I understand. So if he means that what to do when the preprocessing needs to be different for each subject?
For each subject, yes, exactly. Is the process the same?
Yes.
So is
Exactly. So you cannot use, in that case, so this slide that we are looking at, you cannot use this, of course, on all the subjects in a batch, because this applies exactly the same preprocessing to every subject. In that case, if the user needs to apply different preprocessing options to different channels, then I would recommend to do so really individually. Like you can obtain a substats. So let me think. Actually, depends. So if only the preprocessing is different, but then from hemoglobin on is all the same, maybe the user could apply preprocessing separately for each subject, and then append each subject hemoglobin concentration states, and then on this cumulative data structure, then you would run the first level statistics. But in any case, even the first level statistics, you can, every subject is independent, so you can obtain it on each individual independently, and then later on there is a function in the NIRx toolbox to append together the results of the individual first level statistics. And I don't remember from the top of my head how the function is called, but I'm sure there is a function to append single subject statistics altogether. So you would have to run the preprocessing individually and then append everything at first level. Yes, definitely.
Okay.
There is no other
perfect.
way.
Okay.
Yes.
The next question we have, would you recommend to report the results of both ANOVA and mixed effects models, or only one?
Okay, so here so if we're talking about ANOVA, I'm not sure what the user means by ANOVA, because if we're talking about the ANOVA the way I've shown, this is the ANOVA on the output of the mix effect. So for users, for example, using, I don't know, also SPSS, I think you are familiar with the fact that when you run a mixed effect model, you get out a table of an F test for each effect, condition, group, age. So this is the ANOVA. So this module that I've shown is mixed effects plus ANOVA on the mixed effects. This you need to report, because this is what gives you main effect of group, main effect of condition, interaction effect. And then you need to go further and follow up on those effects that resulted significant from this first step. In that sense, yes, you need to report first the ANOVA and then the post-hoc tests. But if the user was referring instead to using, because at some point, it's my doing actually, because I made this slide ANOVA versus mixed effects. So I think this actually warrants a clarification. So when I made this slide, let me go there on the ANOVA versus mixed effects. Let me see if I find it. What I meant is running an ANOVA directly on the data without modeling. So you can, of course, you can run an ANOVA directly on the beta values. You specify this is my response variable, and I want, these are the labels of the groups, and I want an ANOVA two by two conditions, two groups. I want a 2x2 ANOVA. This is what I meant here. So the ANOVA without the model is what I meant in this slide. So I don't recommend it, especially if you have a more complex design, or for example, you have repeated measures. So you have within subject factors, you have different covariates. In that case, I recommend mixed effects plus ANOVA on the mixed effects, which is what I shown in the walkthrough. What I mean in this slide is ANOVA directly without mixed effects. Is it clear?
Yes.
Yes, perfect.
No, because I understand now that I made a bit of confusion here, maybe, yeah.
Another question would be, which is the best way to take into account both the intra-subject and inter-subject variability on the second level?
Okay, so
that's a difficult one.
This is where the curve starts getting steep. No, I'm joking. No, so I think so. Basically, all the variability related to the subject can be modeled with random intercepts and random slopes. Basically, with the random intercept, you want to take into account the fact that each individual subject respond differently, have a different starting point, but then they respond the pattern of response to the two conditions is basically the same. So for example, so in one of the resources that I pointed out, this is explained very well. So basically the slope is the same. Let's say you have condition 1 and condition 2, and the activation is always higher for condition 2 rather than for condition 1. Then each subject will have a different starting point, but for all of them, the condition 2 will have a higher activation than condition 1. This is a random intercept. You are allowing the subjects to have different starting points. With the random slope, you are also allowing the subjects to have different slopes. So it can be that one subject respond more to one condition and another subject responds more to another condition. This is the random slope. And clearly the random slope and random intercept model is the most general one. So often it makes sense to include both. So if this is what the user was asking, then this is the way to go. But again, check the fit of the model with the criteria that I mentioned, the ASC, the BIC, but there are also other criteria that you can check, because it doesn't always make sense. It doesn't always improve a lot the model to include also the random slope. So it is the most general model, but you have to check that it actually yields a greater an advantage, yes, in terms of fit. I hope this answered the question.
Yes.
Yes. Our next question, we got a wonderful presentation, lots of great feedback. So thank you very much, Jessica. You're doing very helpful work here. This question is, can you elaborate a bit more on the role of the dummy coding that you did? So like why exactly you did that? Yeah.
So yes, this is where the learning curve is impossible. No, I'm joking. So yeah, I don't have a very good. So the thing is, the dummy coding is basically it needs to be done because the model originally the model is a regression model, so it tries to treat every single factor that you enter as a continuous variable. But of course, if for example, in this case, we had condition A and condition B, it's going to be 0, 1, 0, 1, 0, 1 time series. And if the model tries to treat this as a continuous variable, it may make, it may be a problem. So basically, the dummy coding is only a scheme to tell the model that they are categorical, that the factors are actually categorical, and that there is a level that is going to be taken as the reference level, because of course the linear it's still a linear regression, so it's going to try and find differences between the two levels. Okay, so you have to tell the model which is the reference level, and the model is going to fit as to give you the answer with respect to the reference level. So it needs a reference. I am aware of the fact that this explanation may not be 100%, so I really recommend you. So it is very well explained again on the FIT LME web page. It is explained, and yeah, we can follow up more on this if you need more practical information. Because I'm aware that this may be a bit difficult to explain at this point.
No, but that's still very helpful, and you know, that research, like you said,
it's about setting up the reference level, because it always the results of the model are always explained in terms of deviations from the reference.
Okay, so questions are coming in, and I think, so thank you so much, but we will definitely not be able to cover them all. We'll try to do our best. So maybe, I don't know, Jessica, if you're sweating already, or we can do a few more, but let's keep it, let's keep it, let's say 2 more. So I'm sure you understand that we cannot cover the many questions, but thank you so much for the interest. So the next one would be subjects have 3 different runs, and between the runs, NIRS was calibrated. So we have independent data sets. So basically they redid calibration for one subject, and they have 3 different recordings with different calibration values. What they're asking is if runs can be compared among each other. For example, run 1 versus run 2 using fixed effects, and if fixed effects is available in Brain Analyzer. And yeah, this is a question that I actually want. Sorry, I wanted to bring up, because we often receive the question of, you know, different runs and a calibration in between, and we always advise not to merge these data sets, because then of course you may create jumps, but to analyze it independently.
Yes, exactly. I mean, so the fact that they are so the fact that they are calibrated in between means basically that it's a new set of calibration parameters, right? So it's
exactly. Exactly, yes. And you know, so, the raw data will have different values. So they're yes.
Yeah, so yeah, this is one of the cases where I was saying that you can add a level of hierarchy in this toolbox, because this is definitely, I would also recommend to keep them separate and add session as an additional factor. And in this case, this would be a within subject factor, because if I understand correctly, each subject undergoes 3 different runs. So it's the same subject, it's a repeated measure. So yes, it's a within subject factor, and yes, you can just enter session as a fixed factor in the model, and also in the random term session. I don't know what's the math operator name there, like session by participant, basically, and that is how you say that you have 1 session per participant. You have you have all participants underwent the same different sessions. So this is how you define a within subject design. Yes, but definitely different runs.
Okay, and we've got our last question here. It's a bit of a long setup, but it's all very clear here. So if a study is looking for the specific effects of aging, is it necessary to add age as a regressor when the group selection is already based on age? The age range may be as wide as 20 years, the 2 groups being 20 to 40 and 60 to 80. Although this question is not exactly related to second level analysis, but in the same study, should DPF or PPF be adjusted for the group?
So I would say, so before knowing the age range, I would have said that since it is already taken into account in the grouping, the age wouldn't make much of a difference. But since it's 20 years, so 20 years is quite long, it's not really in the 20 to 40. I hope, but maybe in the 60, what's the 60 to 80 or 40 to 60,
to 80.
Maybe there is an effect. Yeah, maybe there is definitely an effect of age even within this group. So even if the group is already formed. So yeah, I would definitely recommend taking this into account and checking the fit of the model to see that I would anticipate that it is it makes sense, and I would anticipate that the fit improves. And I mean, in any case, I think it is also of interest in this case. It's not, as I was saying at the beginning of the presentation, it's not only something that you do when you want to control for a variable. It can also be that it is of interest, right? So in this case, I think it could also be of interest to the researchers to get also the effect of age within the groups.
And then
I don't. Maybe you asked the second part, but I don't remember.
The BPF and the PPF. Yeah.
Okay. Yes. So I think in NIRS Lab we use like 6, 7, 6.3, 7.2, and the 6 is the most used DPF. But at the same time, I think that with since the participants are spread across a quite large age range, because considering the two groups, and there is this paper from Scholkman where they introduced an equation for computing the DPF depending on the age. Now the equation, I think, was valid only for the forehead, but still I would imagine that yes, age makes a difference here. So maybe yes, it makes sense to adjust the DPF and or if anything, at least assess the difference in terms of like how different would the results be with and without the adjustment, because this could also be informative, right?
I definitely wanted to say the same. So there is quite some, significantly different results if you use different DPF. And if the age range is very small, it wouldn't make sense. But in this case, as you said, it's 20 years, especially in the group 60 to 80, there may be a significant difference. So the question here was, should DPF or PPF be adjusted for each group? I would actually adjust it even to each single subject. And I don't know if Jessica, what you think of that. But if you definitely add then the covariate, if you add the age as covariate for each subject, despite the fact that you use two groups.
Yeah, sorry, go ahead. Yeah, no, I meant that. No. I meant that.
Okay, so definitely adjust it. Then for each single person, we would have a different, very simple subject, we would have a different DPF and PPF value. So I don't know what, we already have a calculator in NIRS. So I think it's exactly the paper that Jessica mentioned that lets you input the subject age, and it will output you the DPF and PPF. Sorry, not the PPF, in this case the DPF. You will have to then to normalize to get the PPF, but you can already get it calculated through NIRS.
Yes, I think yes, it's the same formula. It's that formula I was referring to. Yes, it's based on this paper, and I think it makes sense absolutely. Individually, not on a group level, like individually calculate the DPF and enter it.
Okay. Yeah. Ashley and Blanca, do we have any other questions or?
I think we can end it on that.
Yes.
We can maybe follow up with some of these final questions.
Exactly. We have received many questions. Thank you very much. We will try to follow. We have your, of course, contact emails, and we will try to follow up. We are not sure if we will be able to follow up with everyone. So again, thank you so much, Jessica. This was really helpful. This was a topic that that it's always been neglected somehow. You always do. Everyone focuses on first level, and then second level. Yeah, you just do that, and you know it's really great to be able to look at more in detail. Before closing, I just wanted to mention that we have a lot of webinars already scheduled. So please take a look at our website. So we have 2 webinars on Turbo Satori, so our real-time our real-time software, so for real-time near feedback or BCI, which is, I think, on the 22nd and 27th of July. Then we have a series on EEG and fNIRS that is happening in August. So we have the first one on the 11th of August and the other one on the 18th of August. And then in September, we have a webinar on infant fNIRS. So fNIRS for studies on infants with rooted care brain. So you can find all details and registration links on our website. Thank you so much. This was really great. Thank you so much for participating. And as mentioned before, you will all receive the slides, and the recording will be available in our Help Center. So give us a few days just to download it and process it, and we will upload it to the Help Center. Okay, perfect. Thanks so much.
Yes, thank you so much.
Thanks so much, everyone.
Bye, everyone.
Have a great day. Yeah.
Bye-bye.
Bye-bye.